Hi everyone, thank you all for coming. Hope you had a good lunch. Yeah. Relaxation workshop. So I decided I'll talk about a recent paper I wrote, which has an integrality gap result. And since there's many of you who are wizards at this thing, there's an open problem of whether that can be either improved or met with a better algorithm. And what I'll talk about is a class of problems that I got from my co-author, speaking of which, my co-authors are Jenny, who's a graduate student at CMU with me. Rajmohan and Ravi Sundaram are professors at Northeastern University. Rajmohan works quite extensively on these content delivery networks, so these problems are from that area. Okay, so my talk has 3 parts. Yes, and yeah, several Ravis here. Yeah. Okay, there are several, that's true, actually, Ravi used to be at Akamai. Thanks, Michelle. Yeah. So first I'll define the problem, I'll show you that integrality gap I promised, and then I'll show you the one special case where we can improve that to a constant factor approximation algorithm by a reduction, and that'll be it. Okay, so what's the problem? We have a graph, an undirected graph, which I'll call a host graph. It has costs on the edges. There is a demand graph which specifies pairs of terminal nodes as its edges, okay? And here's the new twist. Every terminal builds its own network. So I'm not building one network, every terminal builds its own network, okay? And for now, I'm going to assume that the networks that each terminal builds is either a tree network or a star network, okay? You should think of these as virtual private networks built by these autonomous systems, whatever. Now, what is the goal? For any terminal node, the network it builds must be rooted at that terminal node, right? That's why it's that terminal's network. For any demand pair ST in the demand graph, the 2 networks represented by S and T must overlap. In other words, these are networks, these are terminals that want to talk to each other by building these networks, and the way they'll communicate with each other is by building networks such that they overlap at some node where this information is being exchanged. Okay, and finally, I want to minimize the total cost of all the trees or stars built. Okay, so I think I have a picture. These slides are Jenny's, by the way, so all credit to her. So here's a demand graph. It's bipartite. In this case, we have orange and green nodes, and these are the pairs that need to connect to each other. And here's some underlying host graph with other Steiner nodes that are not in that picture. Okay, and one way you could build this solution is A builds that single edge, that second guy builds both, and the third guy builds this edge, and B then builds that edge, that middle guy builds that edge, and this guy builds this edge. Okay, so in this case, actually everybody is just building stars, okay, and every pair that needs to talk to each other like A and B, this guy star and B star intersect somewhere, they overlap, okay. So the name of the problem is design of overlapping networks. We also call it the Dawn problem, Dawn Wagner being one of our good friends who helped fund this research, by the way. So, all right, so that's just a side. Okay, all right. So we also call the version of this problem where we only have a bipartite graph as the publish-subscribe problem. In fact, this is the original problem that Ravi and Rajmohan had come up with. Basically, there are content publishers and there are content subscribers, and they'd like to build virtual networks where they push and pull information respectively. And the reason that these networks have to overlap is because there'll be these hubs from where that information network will happen, transfer will happen, okay? So in this case, we think of one side as publishers, the other side as subscribers, and for now, let's assume that all the nodes on the publish or the subscribe side, right, are building the same type of network. They're all building trees or they're all building stars. Okay, so that gives us to actually 3 types of problems. Both sides are trees, both are stars, or it's a tree-star problem. Okay. All right, so there's a lot of previous work. I'll highlight the main ones here. For the case when you have both sides being trees or both sides being stars, there is a log n approximation algorithm. Can you guess where it comes from? No? Try again. Metric problem. You've got a graph with costs on the edges. I'm trying to build a network. The cost is the sum of the cost. Tree embeddings, right, yeah. So FRT gives that. So this paper by Chakinala et al., Rajmohan is a co-author in that paper, shows how to solve the problem within a constant factor for trees, and then lifts it to arbitrary metrics. There is a relation of this problem to two spanners that you can find in the, two spanners are subgraphs that, approximate distances within a factor of 2 in an undirected graph. This problem is closely related to the virtual private network problem, the VPN problem, a connection I'll point to a little later. And I will reduce some of the versions of this problem to facility location, which is why those references are relevant. Okay, so we'll get to that. All right, so now I'm going to show you perhaps the most interesting result in this paper, which is an integrality gap for an LP. Okay, so how do we write an LP for this design of overlapping network problem? Let's assume we are building trees, right, for everybody. Okay, and it's a bipartite graph. Okay, so first of all, suppose RS is a demand pair. Okay, we want R and S to overlap at some node, right? So let that node where they potentially overlap be called H. Okay, and XRSH is an indicator variable which would be 1 if they overlap at that node. Okay, so this constraint says you got to overlap somewhere. All right, now YRH is an indicator variable that says whether R's tree gets to H. Okay, so these are the usual facility location like constraints. It says, look, if R and S have to meet at H, then R better go to H and S better go to H. Right? That's what this constraint says. Okay. Finally, if R goes to H, right, then it's actually got to cross some cuts. Right. This is that cut cover constraint. Think of a cut which has R inside it, okay, and H on the other side of it. Okay. Then you have to cross the cut, but you only need to cross the cut to the extent that you got to get there. Okay, so very natural is the first LP you will think of, right, if you're thinking about this problem. Okay, so we thought, okay, it's a fine LP, we should round it. We tried and tried, but we could not round it to get a constant factor approximation algorithm. And instead what we found is that this LP has a log n integrality gap. That's what I want to show you. Okay, so let me show you now the basic integrality gap construction. At least log n. Thanks, Michelle. Yeah. This thing stopped working. All right, now it works. Okay. So the integrality gap is going to be a reduction from the group Steiner tree problem. Let me show you a picture. Okay. So in the group Steiner tree problem, we have a graph, an undirected graph with costs on the edges and a root. And we are given a bunch of subsets of vertices that we'll call groups. Without loss of generality, you can think of them as being disjoint. Okay. In this case, I have two groups. Okay. And the goal in the group Steiner tree problem is to build a tree that goes and meets at least one terminal from each of the groups. So it's like a set cover union Steiner tree. So think of it that way. I want to cover each of these sets, but what I'm covering with is a tree. Okay? And this problem has a log squared k integrality gap. K is the number of groups, okay, for a similar natural cut covering LP relaxation. And this integrality gap works even if the underlying graph is a tree. Okay, and that's due to Halperin, Krautkammer, Arvind, Wang. Okay, and I'm going to use that integrality gap construction to build a larger Dawn instance, which is going to have this at least log n integrality gap. Okay, so how do we do that? Well, apparently these things come up a lot in these reductions. I'm going to start with the hypercube. This is the largest hypercube I could put in 2 dimensions. Okay, so in every coordinate of the hypercube, every coordinate of this hypercube, I toss one of the copies of my hard integrality gap group Steiner tree instance. Okay, so I have 4 copies here when I have 2 groups. Okay, by the way, in general, the dimension of the hypercube is going to be the number of groups in my instance. Okay, so that's where you'll get one of the logs going down. Okay, so now what do I do? How do I connect these instances up? Along dimension 1, I'll connect up all the nodes of group 1 using 0 cost edges. And along dimension 2, I'll do that for. Okay, and that's my instance. Now, who are the pairs that need to talk in my group, in my Dawn problem? Well, they are exactly the copies of the roots. And which pairs need to talk? The pairs that are related by an edge in the hypercube. Okay, so in this case, the demand graph is this guy wants to talk to this guy wants to talk to this guy, right, and so on. Okay, so that's the whole reduction. Okay, embed a copy of a group Steiner problem with k groups into a k-dimensional hypercube. Okay, and then the demand graph is a hypercube, and along dimension I, the group I vertices are merged. Okay, so if you start with k groups, you need 2 to the k copies of the original underlying graph. So that's why we're going to have to start with a smaller group Steiner instance. Okay, so we need 2 inequalities to show integrality gap, lower bound. We need a bound on the LP optimum, and we need a bound on the integral solution of this transformed instance. So the fractional one is pretty straightforward. In the fractional group Steiner problem, we construct a fractional tree which sends, if you like, a flow of 1 unit to each group. Right? You can think of the LP as installing like capacity on the graph so that it sends 1 unit of flow to each group. Okay? There's a connectivity of 1, right? Because the cut covering constraint by Menger's theorem are dual to that. Right? Okay, so what do? We just plonk a copy of that LP solution, right? And now you can see all the cuts are covered. In particular, I can send 1 unit of flow from this guy to this guy, right? By sending it to this group and then identifying it and going back. Okay, so there is a flow of 1 unit, therefore all these cut cover constraints I set up are satisfied. So the copy of the LP solution is just is at most 2 to the k times the copy of the LP solution for the group Steiner problem. Okay, now let's do the more interesting case. An integer solution, unfortunately for this problem, each guy may have built a tree that goes into all of the other copies here and there. Right, so there's the only sort of wrinkle in what to do. Well, what we do is we just retract the tree. Okay, how do we do it? We look at the portion. Let's say I want to figure out this is the copy rooted at this root. I see that this guy has a portion of it in some other copy. Okay, so I delete the copy there and I put it in the top copy. Okay, then I look at this part. Oh, I've got a copy of this thing, so I put this part up there. Okay, and I delete this copy. Okay, and I do the same thing. Okay, all right. So that's the retract of the integer solution that we get from the Dawn solution. Okay, now here's a key observation. For every demand pair which needs to connect in dimension I, either R's retract or S's retract has to go and hit group I, right? Because that's actually where they cross to the other copies. Okay, so either if R and S have to meet in dimension I, they're an edge in the hypercube in dimension I, one of their retracts has to actually go and hit that group. Okay, that's great. So on average, you will basically hit half of the groups that you're supposed to hit. So take about, now you can go either way. You can go greedy, as someone said, or you can go randomized rounding. Take 2 log k copies of retracts from this 2 to the k copies, right? And with high probability, you would have covered all of these demands, right? And you can also use some concentration bound and actually get a solution of that value. Okay, so what have we lost? We actually wanted to take only 1 copy of the retract. That's what would have given us the IP solution over 2 to the k, but I've lost a log k factor. Okay, I think we are done, basically. We are set up. So now you just throw together the fractional part. We used at most 2 to the k copies by just stitching those solutions. The integer part I used a little bit more. Okay, and now we have these instances for GST itself, which have the log squared n, but I'm going to have to blow up by a factor of 2 to the k, so the copies I embed will only be of size about log n. Okay, and I'm done. Okay. Sorry, try again. I haven't tried hard enough. I think, yeah, maybe one of you guys can do it. Only in a special case, and you will see, actually. Thank you for leading me into the next part of my talk. Yeah, okay. But any other questions? Yeah.
So that's too much, right? Even if you had to consider a directed version of the relaxation, say it going like Hausdorff sentences.
Right. And then come back in the other, right? I think you would have it there. Yeah, if you have to go back in the other direction, you'll be okay. Yeah. Right. Right. You're only within a constant factor of that problem. Yeah. Okay, so what can I solve in a constant factor? By the way, for this problem, the best known approximation I told you, the tree and the star case had a log n approximation. We just patched up the last case, the tree star case, and now there's a log n in general for this problem. Okay, but we can't do better than this for the when the demands are general. Okay, so we actually don't know how to get a constant. We can get a constant when the demand graph is complete bipartite. Okay, so now actually when the demand graph is complete bipartite, remember the graph is complete bipartite, it doesn't mean that each node on each side is the same. So there can be trees and stars on the left, trees and stars on the right. But heck, if you can solve one of these three instances, you'll be fine, right? Because you can decompose a problem you have, it's a complete problem, right? Into one star problem, one tree problem, one tree star problem, one star tree problem, right? The union of those four will actually give you a solution to the complete bipartite demand case. Okay, so what I have to solve to get a constant factor approximation is these three subcases, right? It's a complete graph where the left nodes, the publishers want to build trees, the subscribers want to build trees, same for stars, and then one guy wants to build stars, one guy wants to build trees. Okay, the reduction to the connection to the asymmetric VPN problem, right, which was sort of roughly alluding to, I think, comes from the tree case, and I'll get back to this connection towards the end of the talk. I just want to show you these two reductions because I think they're kind of interesting. Okay, how did we get this reduction? So in one case, I'm going to reduce it to what's called connected facility location. In another case, I'm going to reduce it to uncapacitated facility location. Okay, so I claim that instead of solving this design network problem, I can identify some nodes to be facilities, and you can build a facility location, and I can recover back my solution. Okay, and then I won't show you this, by combining these two, you can get a constant factor here too. Okay, so what's the problem? Remember, both sides, it's a bipartite demand graph, it's complete bipartite. Everybody wants to talk to everybody else on the other side. Okay, and let me assume that both of them are building trees for this case. Okay, and I'll just sort the publishers and the subscribers in increasing order of cost in the index. Okay, let's also assume, since it's a symmetric case, both are building trees, that the cheapest subscriber's tree is shorter than the cheapest publisher's tree. Okay, so how does the reduction work here? Well, this is the cheapest subscriber. His tree or her tree is the shortest of all. Okay, and now what do I do? Well, I want to convert this to a problem where roughly everybody is building the same tree. Okay, if I convert it to a problem where everybody is building the same tree, then it's sort of like doing connected facility location on that tree. Right? Everybody's building that tree, and everybody else just wants to go to that tree. Right? You will all agree that the best candidate for that tree is the cheapest tree. Right? It's the one among all of the trees that everyone has built. Okay, actually you see why? Because any other subscriber, right, can build a direct edge to the cheapest subscriber by going through some publisher that it has to connect, say P1. Remember, it's a complete bipartite graph, and then back from the publisher to this first subscriber. Right? Therefore, by paying my cost, this guy's cost, and back there, I can get a direct edge from here to there. 3 times my cost. Okay? My cost is larger than or equal to this guy's cost. So within 4 times my cost, I can reorganize my tree to just be a direct edge to the cheapest guy and a copy of her tree. Okay? So that part's good. Okay? So that's the argument here. SI takes a copy of its tree, a path through P1's tree, the cheapest tree, and back. Okay, all right. So now it's clear. Now, actually, there's too many words. Okay. So what's going on here? So if everybody here, every subscriber here decides to go here, right, and build a copy of the tree, right? Now, what do the publishers want to do? They're all going to the same tree. So they'll just take the cheapest direct edge to that tree that everybody builds. Right? That's the assumption.
No, smaller than SI.
Oh, smaller than SI. Good question. Do I not need that? No, I'm actually, the path I'm finding from No, S. You're right, yeah. That's probably what I wanted to say, yeah. So let me just swap this and go to the other side, right? I mean, all I need is one tree that everybody can afford to go to, right? Then I can do it, yeah. Thanks, Nikhil, yeah, okay. Okay, any other? Okay, all right, so what tree am I building? I'm building everybody is building an edge and a copy of this tree, all these guys. Everybody is building a direct edge to this tree, right? So that's connected facility location, right? Like as long as I assume I know who this guy is, who the root is, right? I'm going to build as many copies of this tree as the number of guys on the left side. Okay, so that's my multiplier. So the connected facility location problem, I point to a root and I point to a multiplier, which is how much costlier the tree is going to be compared to the connections coming in. And everybody just takes the direct connection to that. Okay, so that's our problem. Okay, there's like many names for it. We call it tree-star access network. It's also called rent or buy, I guess. All of these. All right, so you got the tree case, right? The tree case. Oops. All right, so for the tree case, we reduced to a connected facility location. How about the star case? This is a little more tricky. Okay, you have to be more watchful. Okay, so don't let me slip anything through you here. Okay, all right. So again, let's sort the networks in increasing order, right, on both sides. Okay, tentatively, let me assume that S1's tree is cheaper than P1's tree. Okay, all right. So now we do the usual facility location trick. Okay, and remember that trick. You start, again, in facility location, you typically go in increasing order of cost. So that's the way I'm going to go for the publishers, okay? So I take the cheapest publisher, okay, and then I nix all of the other publishers whose stars intersect with it, okay? Because I'm going to bear responsibility for all of those guys here, okay? So that's going to be P1, okay? So then I'm going to go to the next publisher, which is disjoint from the first publisher's star, okay, and then I'm going to get rid of all the other guys who overlap with this. Okay, so I'm going to form clusters of publishers. Okay, so all these guys overlap with P1, so they're all going to be. So these guys are all going to be part of P1. By the way, I'm looking at an optimal solution. I'm sorry, I should have said that. Okay, I'm looking at an optimal solution. I'm going to show how I can reduce it to a metric facility location problem. Okay, all right. So I got. The cluster of P1 has got this, the cluster of P2 has got this. Okay, all right. Now what do I do? There are two cases, okay, and it's slightly tricky, but not too much. I'm now going to look at each of these clusters that I got. Remember, the clusters are cheapest facility that star I could find, plus everybody that overlaps with it, not overlapping with anyone before. So I look at one of them, okay, and I know that this guy has to overlap with the cheapest subscriber, S1, somewhere. Okay, let's call that point, I don't know what it's called, HI, okay? Because this is PI, okay? HI is the hub where it meets S1, okay? So the two cases are the following. We look at the direct edge from S1 to HI and check whether it is costlier than the whole star that P1 builds, PI builds, okay? And the other case is going to be that it's cheaper. Okay, so there's only two cases here. Okay, I look at the single edge. If the single edge is costlier than this whole star that PI builds, okay, then PI looks like a really great candidate to send everybody to. Okay, so what I'm going to do is to send all of the other guys in its cluster to PI. Okay, that's easy to do anyway, by the way, because this is the cheapest guy, and then I went to everybody else above him who is costlier than PI. So they're all going to go here. But I'm also going to go from every SI to the center of that PI. Okay, how can I afford that? Okay, so we have to be careful about that. So this is what I'm going to do. All these guys are going to go there. By the way, this is almost costless because I'm going to pay twice my cost to get there. Right? So this part's okay because I'm ordering by the cost of the stars. How do I pay for the cost of getting from each of these subscribers directly to PI? Okay, so well, let's take a look. Now let's actually change our orientation. Okay, let's think of ourselves as being one of these subscribers. Okay, how much in total do I pay to shortcut and go into one of these PIs? Well, I pay the cost of my edge to the hub And then from the hub, I pay a cost of pi star. Okay, so if I sum that over all of the PIs which are building hubs like that, worlds like that, right? I'm paying the cost of each of those edges going to those hubs. But this is the reason why we picked these hubs to be disjoint, remember? Right? I can't, two of these hubs that I picked to form clusters don't intersect with each other. So the set of edges where I go to meet each one of these clusters are disjoint. Okay? Therefore, each time I pay the cost of that guy's star, but the number of times I pay, each time I only pay the cost to the corresponding edge of S1 to that corresponding hub. Okay? So in total, if I take any one of these subscribers, the total amount of overhead that I've spent in trying to connect myself directly to here is upper bounded by the cost of S1 star, but I'm just any other subscriber, so I'm costlier than S1 star. So all of these extra can be charged to that S1 star. Okay? I think the most trickiest argument in the whole bit. Okay, so good. So when I have the case that this edge alone, that single edge alone is costlier than the whole publisher's star, I'm able to pay for everybody just paying one copy of my star. In the other case, that is when this guy's star is costlier than that edge, okay? I think now what we do is send everybody to pi, as we did in the very first reduction, okay? So in that case, let's see. Sending the stars from here through pi to S1 costs me, well, this guy goes through pi, and then from pi it goes to S1. Okay, and that last edge that pi took to go to S1 is actually cheaper than the cost of pi. Okay, so therefore I can pay for the 3 hops that I made to get here just using 3 times my cost. That's this one, right? And all of these guys, they can easily connect to S1 through again via this pi. Okay, all of these guys, we know that they all form, they all meet pi somewhere, so it goes to pi, goes in through there, and comes back. Okay, so in the first case, we send everybody to the center of the cluster. In the second case, we send everybody to the cheapest subscriber. So in fact, what we are doing finally is depending on which case the cluster falls in, right? If the cluster falls in case 1, we send it to the center of that cluster. If the cluster falls in case 2, we send it to S1 for the sake of all these guys. And where do all the other guys in these cluster go to? Well, depending on which case they were in, they either go to their own center or they go to S1. Okay, so I've transformed the problem I started with, the star-star problem, into a solution within a factor of 4, I think, somewhere I used it, right? Into one where everybody connects to either one of the PIs or S1, the cheapest guy, okay? What's the cost of, and everybody else just connects to the closest guy like that, okay? So I would think of connecting to one of these guys as opening a facility there. How much is the cost to open a facility there? Well, I know wherever I open a facility, I'll have to connect all the subscribers to it. So the cost of opening a facility anywhere is the cost of these green edges. Okay, that's the uncapacitated facility location problem. Okay, so at each one of these nodes, the cost of opening a facility is the sum of connecting all the subscribers to that guy. Okay, and once it's opened up, anybody else can connect to it. Okay, so I've reduced this to an uncapacitated metric facility location problem, solution factor of 4. Okay, so moral of the story, in either case, we can sort of reduce it to opening a facility in one of these places, and we have reduced our problem. And as you can imagine, when I have both trees and stars, we do one of the two, depending on whether PI is bigger or SI is bigger. We can either build a connected facility instance. Okay, of course, the algorithm itself will have to guess where S1 is, right? And in one of the cases, and it'll have to do the corresponding things. Okay, so that was a long constant factor bit. Here's finally the relation between the tree problem and the asymmetric VPN problem. Now, some of you here are experts in asymmetric VPN. For the others, let me just tell you what the problem is. In asymmetric VPN, it's asymmetric because there are publishers and subscribers, in my terminology. The publishers are the guys who want to send outflow, and subscribers are the guys who want to take inflow. Okay? And every node has a demand value that it wants to send out or in. And the asymmetric VPN problem wants to build one network, not a collection, just one network, such that any flow, such that it obeys the bounds of how much each subscriber can pull and how much each publisher can push, right, can be routed through this capacity that we have apportioned. Okay? So that's what the asymmetric VPN problem is. Okay? It has a constant approximation. The nice thing is the approximations deliver a solution which is a tree. Okay? And so what we do is we use these two observations. Right? First of all, the union of all the trees that we build for our tree problem can be converted into a solution to the asymmetric VPN problem, right? Where the demands are all +1 or -1. That's one part. And conversely, any tree solution we get, which luckily happens to be the case for the approximate solutions we get, can be decomposed into a bunch of trees, one for each guy in this publisher and subscriber sets. Okay? Therefore, just because we were lucky and got this tree solution, we are able to get back to it. But it's actually not clear whether these two problems are really the one and the same. It could be, for all I know. I just can't prove their equivalence. Okay? All right, so obvious open problems. Can one of you improve the integrality gap? Can you convert it to a hardness of approximation? Right? Is there a similar integrality gap reduction where one of the sides is building a star? Not, remember I used the group Steiner tree on both sides. Okay, I don't know. And finally, this last problem I asked about whether asymmetric VPN is really the same as this problem. Right? Okay, so I just told you 3 things. You should remember what the problem is. You should remember for the tree version, there's a log n integrality gap. And for special cases of complete demand graphs in the bipartite sense, we are getting constant factors. Thank you for your attention after lunch.